Welcome to this third session of storytelling, and today's session topic is cancer therapy through Linux. And in this session we have two speakers, and they are, one of them is the developer and other is the user agency. So, and we have our friend, colleague from DIT who is coordinating this program since long, Mr. R.S. Burma, scientist staff and additional director working in this department and coordinating this particular program for a longer time. We have Mr. Amol Bhagwat. He is a senior scientist at Samir Mumbai, and coordinating this particular program through medical electronics division. And he has been involved in this program from the very basics, and which involves design, development, deployment, and he has also taken it till technology transfer level. Then on the other hand, we have a definite user, Dr. G. Selva Lakshmi, professor and head of Department of Radiation Oncology, Cancer Institute, Adyar, Chennai, who has been treating the patient for the past almost 20 for so many years, and she has got a very large experience of 29 years in this field. She has completed her basic MBBS from Stanley Medical College of Chennai, and later joined Adyar Cancer Institute, Chennai in 1987. Since then, she has been serving this institute. A department, as of all of you are knowing, that apart from other tasks, R&D is also very integrated job of the department, in which we are conducting research in many areas of applications, industrial applications, medical electronics, agricultural electronics, microelectronics, and so many areas. And this particular development, Liner Accelerator, has been done under medical electronics division of the department, and it has been successfully developed, completed, and also deployed in a large number of places for treating the patient who are suffering with cancers. And as all we know, actually this particular machine is currently is not available from the Indian sources. This is the first, I believe this is the first machine which has been developed indigenously by our R&D organizations in India, mainly the Samir. And this is a very challenging field, in which actually various field of technology, electrical, electronic, mechanical, civil, IT, and all other, they have joined hand together, and finally a good product has come with the 6 MB range of Linux, which is currently used in cancer hospital in Adyar and also one or two more institutes in the country. And this technology now has been transferred to one of the manufacturers in our country, who is trying to commercialize this technology so that it's available to all user agencies at a affordable cost, and it can be put to use at different hospital and by used patients, or different kind of patients. With this, since our colleague from the department, Mr. R.S. Burma, has been coordinating this particular activity for a longer time, I now hand over the mic to Mr. Burma to conduct the further actions in this.
Thank you, Mr. Tarashankar. As he has mentioned, Department of Electronics, Minister of Electronics and IT is involved in the development of the Accelerator machine in association with Samir, and this technology have been successfully developed and deployed at various cancer research institutes in the country. And after the development of 4 to 6 million electron volt linear accelerator, Ministry has initiated the development of high energy Linux machine to treat the cancer patient. And not only the linear accelerator, Ministry have taken up the development of complete accessories used for this machine to manage the cancer treatment very effective and very precisely. The accessories, namely the multi-leaf collimator, electronic portrait image devices, radiation field analyzers, and three-dimensional treatment planning system have also been successfully developed. Now, before I hand over further talk on this development, we'll show a video for 3 minutes, and I'll request to the person to switch on the video on the development of LINAC machine.
Medical electronics. Medical electronics division of Samir is involved in the design, development, installation, commissioning and servicing of the medical linear accelerator machines.
At the outset, I would like to thank the Ministry of Communication and Information Technology for allocating Siddharth to the Cancer Institute, Chennai. I think it is very, very welcome change that Samir has taken the honors of producing accelerators, and I think we thank you.
Siddharth is an indigenous computer-controlled 6 million volt linear accelerator with a dose rate of 240 centigrade per minute. Now, as the patient setup is being done by setting up the optical field, we find that the gantry is also fixed at an angle pre-planned during the planning time. Subsequently, the treatment is done from the control room outside. Being an electrical machine, Siddharth has no radiation on beam off, and there is no radioactive waste to be disposed of.
The Cancer Institute Adyar is a premier institution in the country which caters primarily to the lower socioeconomic group of patients, and nearly 50% of our patients have been treated free. Our gift which has been given by Samir to us, the Siddharth, would therefore be very useful in the management of patients. The instrument would be maximally used and also benefit the poor patients.
Thank you. Now I'll hand over further talk on this subject to Mr. Amol Bhagwat to brief on the development of an accelerator in the country.
Good afternoon, and thank you very much Verma-ji and Tarashankar ji from DITI. It's my proud privilege to be here amongst audience here to tell about the development of Siddharth, which is the 6 million volt medical linear accelerator. Now, for the benefit of all, as was shown in the video clip in which none other than Padma Vibhushan Dr. V. Shanta spoke about the use of medical LINAC, it is very clear that it is used for treating cancer patients. Now, as a developing agency, Samir, that is Society for Applied Microwave Electronics Engineering and Research at Mumbai, has been in this field for last many years, and what goes into it is very complex engineering of different disciplines coming together. We have developed in the beginning, late 60s, the first ever accelerator for physics research. From there, we have transferred now into what is being used for applications. An accelerator, like in a car, is nothing but which accelerates. So in this case, it accelerates electrons which go and hit a target from which X-rays are generated. Very hard X-rays, many more times, 1000 times, 6000 times more energetic than what you use for normally a fracture or a dental X-ray. These X-rays are made to fall on the affected part of the human body, and the field is controlled using shutter-like structures called as collimators, so that radiation falls only on the affected region. Now, to accelerate this particle, you require electrical fields which are set up in what is called commonly as waveguides, or we call it linear accelerator tube, which is the heart of the machine. The linear accelerator tube is nothing but a set of copper cavities which resonate at a frequency, and in tandem they push the electron from one end to another, a journey of only 30 centimeters, and in this 30 centimeter journey they gain an energy of 6 million electron volt. With this high energy they hit the target of tungsten and produce bremsstrahlung or X-rays. Now, making this cavity itself is a very precision mechanical engineering job. So it has to be done in a very controlled way. Besides that, we need to join them together in such a way that very high level of clean vacuum is maintained inside it. With this vacuum ensured, and then this kind of a bulb pinched off, you have a LINAC tube which is ready for use, a device which is ready for use. People from the younger generation know about ICs, VLSIs and things like that, or the SIM cards, which are very, very small devices. This is a copper device weighing around 25 kg, and this is powered by microwaves, high power microwaves. These microwaves are generated by a source of power which is called as a magnetron. We all use microwave oven. This is a slightly different type of arrangement. It's a pulsed microwave generator, a magnetron, which generates 2.6 megawatts of peak power. The microwaves are then sent from one end, that is the source, up to the tube's window, LINAC tube's window, RF window, which sets up the accelerating field. So with this kind of a field setup, the electrons are ready to accelerate. So they are pumped into that and they get accelerated. Now to power the magnetron, we require a source of electrical power. So because the efficiency of the magnetron is around 45 to 48%, we require little over double the power to power the magnetron. So this is not switched on continuously as done in a microwave oven, but done in a pulsed form. So there are high voltage pulses of 48 kV, and the magnetron draws about 100 amperes of current in a pulse of duration about 4.5 microsecond. A microsecond is 1 millionth of a second. So in that short duration pulse, the magnetron generates microwave power, and such stream of pulses is being fed to the accelerating cavities. So these accelerating cavities, they do the job of accelerating the electrons from one end to another. They hit the target, generate X-rays. Now, a lot of technology, as I mentioned in the beginning, goes into the making of LINAC tube, which is related to very clean environment, high temperature brazing. If you have to do a repair of a stove, then you require temperatures about 300 to 400 degrees Celsius. Here we do brazing in 3 stages. One is the highest temperature of about 1050 degrees Celsius, then few degrees below that, and then the third. This multi-stage brazing, maintaining the vacuum, is a very, very difficult task. And at the same time, if you make a mistake in one step, you have to go back and redo it everything again with a new set of tools. So with this kind of a process technology, which is requiring high precision engineering also at the cavity level or the LINAC tube level, we go on to the magnetron, which is high power microwaves. To generate the high power pulses, we require high voltage engineering, and to control all these things and put it in a place, we require control electronics for precision movement, for precision control of dose, for precision dose delivery. All these things come under precision control electronics. So we find that this is really a confluence of technologies from diverse fields, and all are high technology areas. Having done that, you have made a machine which is now ready for qualifying for clinical treatment or clinical use. My user agency, Cancer Institute representative, is here, Dr. Selva Lakshmi, and she'll agree that she will not use a machine unless it is fit for clinical use. To do that, I have to prove that to her that yes, it is fit. So as you know that human body has 70% water. So we do all the measurements in what was mentioned some time ago as a radiation field analyzer, which is nothing but a water tank, and we do the dose measurement inside the water tank and show that these profiles are behaving in the way it is required to qualify for clinical use. This is done by a third party agency which is regulatory in nature, Atomic Energy Regulatory Board. So having qualified for clinical use, then the hospital user agency checks it for itself for the same thing, and then the patient treatment is started. This is all about the technology part of it. Friends, let me say that having worked for 30 years and 11 years as the head of the division of this activity, it is a very, very perspiring, at the same time inspiring job for all my teammates. Lot of effort goes into not only making the machine, but its installation, commissioning, service and maintenance. And I'm proud, I have the proud privilege of being a part of this team of developers, funding agencies, users, wherein we have maintained more than 90% uptime. On the clinical side, it's my colleague who will answer more questions, and I'll give it the mic to my colleague, Dr. Selva Lakshmi.
Thank you. At the outset, let me thank Mr. Verma, Mr. Shankar and the Samir for inviting me to participate here. Basically, I would like to say that whatever he has been saying about radiation oncology, there are 3 types of treatment for cancer. Basically, it's surgery, it's chemotherapy or radiation. Any cancer patient, about 60% of all cancer patients will definitely need radiation therapy at any part of their treatment. So let us not ignore radiation therapy as such. So Samir has come out with such a big mind or generous mind to give us this particular machine which we have installed in 2008, and we have been going on with this thing for the past 8 years. And to believe me to say that it is equally competent with any other international product which is available. And there is no question of anything that it is, the standard is substandard or things like that. It's absolutely a versatile machine which has been used by all my colleagues there, and we find it very useful. And you know, when somebody is affected with cancer, it is not very easy to tell them to go away. You need to give them some form of treatment. If you really have met a patient with cancer in your life, you would agree with what I say. And not all institutions in our country can afford an exorbitant price to purchase machines which are being traded elsewhere. I'm very much thankful to Samir for having given this machine to us, and we have treated more than 1 lakh of patients on that particular machine. Anything else you want to ask, tell me?
I think for the benefit of the user, you can briefly explain what the radiation therapy is actually. So,
How the radiation works?
yes, how radiation therapy is done.
See, basically, in a human cell, it divides into 2 to develop daughter cells. And you know, in our mouth, you will be surprised. Every 6 hours, our cells get destroyed and new cells are formed. So what happens in cancer, instead of dividing into 2 cells, it tries to divide into many cells of various sizes. So that is basically the division where biologically the DNA is important. So something goes wrong with the DNA. So what happens, this radiation, it goes and attacks the DNA. So it can attack the DNA of cancer cells as well as normal cells. But where there is more division, that is when cancer, there is more division of cells. So what happens, the radiation kills the cancer cells more than the normal cells. Okay. So mainly the attack is on the DNA. If you kill the DNA, then the cell is dead.
Okay.
That is how the radiation works on the cancer cells.
And what happens to the normal cells which also get destroyed during this process?
Normal cells also get destroyed, but they have the capacity to regenerate again.
Okay.
But cancer cells, once killed, because they are all already abnormal cells.
Okay.
So once they are killed once, they lose their capacity to come back again.
And approximately how many patients might have taken advantage of this machine, indigenous machine which has been developed by Samir Mumbai in association with the department?
Basically, we started in 2008.
Okay.
And we have been treating minimum 50 patients, a maximum 60 patients per day on that machine.
Okay, okay. So very nice, really. And my another question is from Amol. Though actually, what were the major technological challenges which you might have come across while development of such a big machine, which involves a large number of disciplines of engineering, especially civil engineering, electrical engineering, electronic engineers, IT, and electronics by itself. So, can you just elaborate what kind of challenges you come across by integrating so many fields and coming out with a very, very successful product?
Sure. But before I answer that question, I would like to add to what Dr. Selva Lakshmi has mentioned, that to date, in her hospital, although 1 lakh patient plus have been treated, overall under the indigenous program, whatever number of machines have been developed in the past, totally 4 lakh exposures have been completed, including the 1 lakh which she mentioned just now. Now to come to the technological challenges or the technical challenges which have been faced in the development, there are numerous, but in the given short time, I would like to mention a few of them. First thing is that making a LINAC tube, as I mentioned, which is ultra high vacuum, 10 to the power -8 torr vacuum is maintained in that. So making a LINAC tube itself is a challenge, first thing. Now, when you want to make a medical LINAC, the requirements become further stringent. You require a dose which is uniform. Earlier it was requirement was about 3% of the symmetry required. That means if you look at any part of it equally on the two sides of the center, it should be, the dose variation should not be more than 3%. Now it has been made 2%. So to get the required symmetry and flatness of less than 3% or 2% itself is a major challenge. Even people abroad have been struggling in the West to develop machines which give the required flatness and symmetry. Now, in the world scenario also, as I mentioned, that the challenge is so much that only two companies in the world are making medical LINACs. Because the complexity and diversity is so much that people normally don't venture into, they are left it to some big players. I don't want to name them because it's already available on the net. And we have also faced difficulties in receiving the required mechanical accuracies in a structure which is weighing 5.5 tons to receive, to accomplish an isocenter which is within 1 millimeter radius sphere. It's a big challenge. So leveling of the machine, making it work every day in and out for 8 years with the same isocenter, not varying outside that sphere, makes it a very rigid structure. That was another challenge. On the high power microwave side, you find that sometimes we have high voltage microwave related problems wherein the field breaks down because of certain contamination in gases. So that is another problem which we have faced. We as Indians normally feel that some of the devices may be great and because they are imported and they are from advanced nations. We have found that they also struggle in the field when we use those devices. They have their own gas leakage problems or failure problems, some of them, not all. And whatever, some of them which we have used, we face difficulties in getting them fixed. Other area of high voltage is that you have on one side high voltage pulses which are very high in power. So in the vicinity of high power, you have very low voltage dosimetry working in the same geographical location. So what is called as electromagnetic interference comes into play. So you have a lot of challenges to make low voltage control electronic circuit work in an environment which has to be necessarily very noisy. So it is like two strongly opposing parties working together for a good cause. So we faced difficulties in that also. Now, last but not the least was in dosimetry. As I mentioned, one of the points was getting the flatness. Getting the required dose constancy, because a medical LINAC is an electrical machine. Day in and day out it has to give a constant dose rate. To get that constant dose rate, this electrical machine has to work in a very stabilized electrical environment. So to create that environment itself, we had surmounted a lot of difficulties, technological challenges. Then you are not able to see the radiation which is treating the patient. So optics is the job of optics is to simulate that radiation field and make the technician see the exposure area before the treatment starts. Aligning this optics with the radiation field by taking a third reference of a mechanical field itself is a challenge. So all these I can sum up as technological challenges that Samir faced and which all other companies also face. I think that probably answers your question.
Really, thank you. Actually, again, one more question. As Madam also said, and you also said, there are only 2 manufacturers worldwide for this line neck machine, and cost is exorbitant as on date. And not only for the line neck machine itself, but cost of treatment as well. So now I want to know what steps you are going to take or you are suggesting to be taken to bring the cost of the machine and ultimately treatment in affordable range of the Indian masses.
Well, I am very thankful to our parent ministry, Department of Electronics and IT, which has taken this initiative of indigenization. That itself has brought down the price. One of the major components of cost is the cost of technological knowledge bearers. That is one component. Second component is the cost of indigenized components which go into the system. So both of these components have come down drastically because of indigenization, and I am very proud to share with August members present here that the cost of an indigenous machine is about 50 to 60 to 55 to 60% of an imported machine for multiple reasons which are given, and the maintenance of this complex machine is also done by those who design and develop it, and therefore that cost also has come down. So this has been a major development, and since we need more machines, under the aegis of our department, the technology has been transferred to a private company in India who are likely to come up in a bigger way in larger numbers, so that more and more hospitals are able to get this machine at an affordable cost, and they will also maintain this machine. So this is one of the major steps which has been taken, and I am very thankful to the department and the government of India that this initiative has been taken so that more and more cancer patients get affordable health care.
I will add further to this. Our ministry have transferred the technology for this machine to the industry, and almost this machine will be available in our country almost 1/3 of the import price. So this is and one very common question I would like to ask Dr. Shelva Lakshmi. After the radiation therapy, what are the side effects and how the cancer cells are killed? This almost it is asked very commonly from the patient or the people who are given the radiotherapy treatment from the machine.
See, basically you have to give radiation without side effects. That is our aim. But the problem is when you are, as I said in the beginning, when you are killing the cancer cell, normal cells also will be killed. So what happens, whatever area you are treating, let's say for example the face. So when you are treating some cancer inside the tongue, so you can't just put the tongue out and treat. You have to treat with the mouth closed. So what happens, this area also gets affected. So the skin gets discolored, and part of the cheek and things like that also will get some changes. But these changes are reversible, but there are some changes which are irreversible also. But these things you have to sacrifice in a case of curing a cancer. That is very clear. So you say take in the brain or lung or liver, it is even worse because we have only one brain, we have only one lung, we have two parts of lungs, and you have only one liver. So you have to live with whatever changes are made. The side effects are not done purposely, but it does come when you are doing some sort of treatment. And I would like to add to what he said about the machine and the parts. You know, these parts, when you are going for an international machine, imported machine, you know, every time you buy a part, say he was talking about magnetron, thinatron, things like that, you know, they have to bring it from wherever they have manufactured it. You don't have to wait, you have to wait for a week till the breakdown is settled. See, here you can immediately get it, they say that you have to ship it, you have to do that, you have to do this, you have an import duty, you have that duty, this duty. You know, here, these things are not very common done.
The audience is having any questions?
Madam, do you have some other program also in the institute regarding this cancer therapy other than the LINAC?
No, as far as radiation therapy, no, we don't have anything
don't.
else. We have 4 Linacs, and we have the brachytherapy machines, and of course we have chemotherapy surgical teams which are going on. Of course, I would like to bring there about the nuclear medicine department, which is an integral part in the where you use the radioactive isotopes for treatment. We do have that along with our radiotherapy department.
Oh, madam, generally such machines which comes into use, especially which have got radiations and all, they have got regulation attached to it.
Yes.
So what are your experiences with this machine which is being used by your staff and technicians and doctors there? How they feel about how the safety about this machine?
So we have a very robust physics department with us, and physics head who is also the person who is the radiation safety officer. He is called the RSO, and he has to answer AERB to the core.
Okay.
See, if you are right, see, no, many people say that many governmental organizations have some hindrance, but it is not.
Yeah.
If you are right, they are right.
Okay.
You need to be right.
Okay.
If you are going to be wrong, definitely he is going to put trouble for you.
Okay.
Because with radiation, nobody can play.
Nobody.
Radiation is a lethal weapon. It can kill an entire country. I think you would have known about Hiroshima, things like that. Radiation can kill a country. So we have to be absolutely safe, and these things are very, very clear, and with this particular machine, I think we have had no problems at all.
Okay, thank you. And Dr. Amol, we have already developed a 6 MB machine, as you said. Do you feel that we have achieved the goal and it's over, or do you need some more technology development in this area to go ahead, or some more R&D work is required to reach further?
Yeah, I mean, we as a unit are always responding to the medical fraternity. So whatever additional features which have now become desired, highly desired features. So in the near future, we would look forward to adding such additional features, because this is a software age and more of software driven things are there.
Yeah.
I must mention here what I probably did not elaborate much about is that in the earlier versions we had hardware electronics controls. So that journey has continued, and from hardware now it is embedded software. We have FPGA control system completely indigenously developed. So we use FPGA control system for which all the software and the hardware is indigenously developed by Samir, Mumbai as well as Chennai together. So, and whatever are the future requirements which come from the user community, we look forward to that. And any other things like Verma ji can tell about it more in the higher energy program of anything. So those things can come in the future also.
Ministry of Electronics and IT, hello, have already approved an initiative to develop a dual photon energy linear accelerator. It's electron and photon, and the almost development work is completed by Samir, and clinical trial for this high energy linear machine is likely to be initiated somewhere in March or April 2017. Now, apart from this high energy LINAC machine, there is a further initiative through this linear accelerator to develop a medical isotope in the country. The isotopes is a small element, is in the form of liquid. The cost of this medical isotopes comes around 22,000 rupees per ml. So might have initiated to develop the medical isotope through linear accelerator energy. In the first phase, there is a plan to develop 20 mmB linear accelerator, and it's going to be tried out, and this is a joint project to be implemented in the country with the Samir and DRDO in mass. So these are the further development related to the linear accelerators.
I think I will now invite some questions from our audience. If they have any question, please.
One question to ma'am, that when the cancer spreads from some part of the body to the liver and lungs, so is there any further possibility for the patient to be treated, or that's the end of?
No, basically it depends upon whether, suppose you have a cancer in the colon, or you have breast cancer which has spread to lungs or liver, then you have to see whether the breast part of it is cured. If it is okay, fine, then you have only something in the liver or lung, you can always give chemotherapy or you can give radiation also to that area. But it all depends upon how the situation is. All the times you can't say you can do this, you can do that. And whenever the disease is spread, definitely the chances are less.
So ma'am, that means when the stage crosses from first stage to second stage and second stage to third stage, so the chances of getting treated through radiation is lesser.
Yes, with stage 1 you can cure 99 to 100%. So with stage 2, 3 and 4 it rapidly goes down to 20%.
What is the possibility at stage 3, ma'am?
It's very difficult to say, maybe about 60%, depends upon which cancer. So you see breast cancer and uterus cancers you can treat even stage 3. But once it comes to other cancers like liver cancer, things like that, it's very difficult when it comes to stage 3.
Thank you.
Any more question, please? I think there are no more question. Anything which you want to add before we closing the session?
Well, as a scientist and an engineer representing Samir, I would like to thank the department and the government of India for having supported this program for past so many years and continue to do so, because this is an extremely advanced technology and there are very few nations working on this. We have been very fortunate that we have a legacy and which we will be proud to continue and serve the people of India. And please support us by funding the Medical Accelerator program and its application, so that we can achieve further heights and serve humanity at large. That's all I want to say.
Thank you, Dr. Mol. And at this juncture, since we have come to close to almost this session, I would like to thank our speaker, Dr. G. Selvalakshmi Madam, Professor and Head, Department of Radio Oncology from Cancer Institute, RDR, for sharing her thought with us and also allowing our machine to be there and continuously giving feedback for improvement, and also kind of actions are required for maintenance and continuous running of the machine. Thank you very much, Madam, and really at a very short notice, Madam has been here to share her experiences with this machine, and the patient have undergone the treatment. And also I would like to thank Mr. Amol Bhagwat, who was working on this machine for a longer time and has been in the field for a very long time and sharing his experience while designing and commissioning of the machine which he has experienced. And he and his team has brought this machine up to this level that today it is available in 4-5 different hospitals in the country and serving the patient for a good cause, and people are getting benefited with this. Also I would like to thank our moderator, Mr. Barma, Additional Director at IT, for taking questions and conducting the session. So with this we have come to end of this session. I will request R.S. Barma to kindly give away a token of appreciation from our side to our speakers today. So please bring us. Mr. Barma, please come forward. Yeah. A token of appreciation to Dr. Lakshmi, please. Thank you. Thank you. Yeah. I will request Mr. Ashok Anamsagar to come forward and kindly give up a small token of appreciation from our side to Mr. Amol Bhagwat. Yeah, sure. Please come. Yeah. Thank you, Verma, and thank you, Mr. Ashok. Thank you very much. So, ladies and gentlemen, thank you very much for kind listening, and we have now finishing the session. Thank you very much.